Welcome back. We are in section 10.2 on rotational speed, and this is 9.2 from your textbook. Tangential speed. There's a word you don't see a lot. A tangent is a line that touches a circle. This is a tangent line to a circle. Let's say the circle is going around in a circle, and I've got a point on this circle right here, and that speed is going straight ahead. How fast is it going? Or if I were to take another place, maybe here, and I ask you how fast this is going. If you've ever seen something going around and around, like the inside of a washing machine, the outer part is going to go faster than the inner part because it has something to do with the distance. There's a speed that the entire disc is going around. So let's say a merry-go-round. The outside is going to be faster than the inside. The inside is where you put the babies. The outside is where you put the older babies. So it's the idea of it's faster. It's going faster. It's tangential speed, or it's linear speed. Speed going in a straight line is based upon the distance, and it's based upon how fast the entire disk is going around. So this is a little bit of review from the last section. Since the center of axis on a record is in the center, then the turntable and the record rotates. If you have an object somewhere other than the center of that, so like the ladybug sitting here, the ladybug is going to revolve around the edge, or wherever that ladybug has to be traveling is going to be revolving around that same axis. So you could ask the question, is the ladybug traveling as fast as she could? Is there any place on the record where she could travel faster? I would say no. The fastest place would be on the outer edge of the record. In fact, there's going to be a pull on her body to even fling her off. As it goes faster and faster, you're going to want to fling off the outside of the record. We'll talk about that's just inertia. But if you were going to want the safest or the slowest place, you would want to go in towards the very center, and then it's not going around very fast. The whole disk is going around at the same speed, but the linear speed, how fast you're going in a straight line, is based on how far away from the center you are. So we'll see that the linear speed, this frontward speed, if you've got a circle here, what a circle, wow, great circle. If you've got a circle and you have any speed, any place on that circle, I'm happening at that instant to be going forward at a certain speed. Well, that speed is going to depend upon the distance from the center of the circle, and that's called the linear speed, the straight line speed. Not the speed I'm going around in the circle, but at that instant, I'm going forward at a certain speed, and that's called its linear speed. I can also call it the tangential speed because this straight line is a tangent to a circle that big. If I were to measure this speed, that's tangent to a circle this big. So, but there would still be called linear speed or a tangential speed. Now, it's important when something is moving in a circle that the entire object is going around at the same speed. That record doesn't come in different parts. It's one solid disk that goes around together in a circle at a certain speed. This is called its angular speed. So let's imagine you've got a circle. How fast is this angle changing? Okay, I'm at 0 at 1 second, and now I'm up here at 45 degrees farther in another second. That's as it's going around and around and around the circle, how fast is that angle changing? That's called its angular speed or its rotational speed. And we're going to call that omega, which is Greek letter O, or Greek letter, it's the last letter in the alphabet. And we're gonna do this usually in terms of a rotation or a revolution. How many times does a dot, say, on that circle revolve around the inside per second or per minute? So, for instance, records were always in RPM. You have 33 and a third. You had a 33 record, 33 and a third record. You had a 45 record. You had 78s. These meant that they were revolutions per minute. How many times did they go around? So anything that spins, and you're going to see that in this world, there's lots of stuff that man has made that's going to spin and spin and spin. The wheels on your truck, you're going to see that the tire distance, how big your tires are, depend on whether your odometer works. You can mess up things just by putting in aftermarket stuff on your car. So how many times does it rotate in a certain amount of time? That's going to be its rotational speed or its angular speed. The other thing that's confusing, I think, since I told you that the linear speed is going to be based on the distance, it may think that any point is going to have a different rotational speed, but that's not true. This is traveling 45 degrees in the same amount of time that this is traveling 45 degrees. The difference in linear speed is the fact that here I'm covering a greater distance in the same amount of time as I covered here. The same angle was displaced, but the bigger your pizza is, the bigger your wedge gets. So that's the idea, that the edge of your record, say, or any circle that's moving, is going to cover a bigger distance in the same amount of time that a smaller one towards the middle is. So that path will have a greater tangential speed, but it has the same rotational speed. Now the math is actually easy. So your linear speed, if whatever this ladybug's tangential or linear speed is, this, if it's twice as far from the center, is going to have twice the speed. Okay, so we'll see that the formula is actually quite simple. It's based upon the radius, how far away from the center of the circle it is. And so if it's twice the radius, then it's going to be twice the speed. So here is the proportion. This is not exactly an equation. We'll see that the velocity, the linear velocity, that straightforward velocity, is proportional to, that's what the squiggle line is, proportional to how far away from the center you are, that's your radius, and omega, which is the rotational or angular speed of the disk. So the whole disk is spinning at so many revolutions per minute, or cycles per second, or something like that, going around in how many times around in a certain amount of time. The number of complete circles in one time, that's omega. And then your radius is how far you are from the center. So the velocity is going to be proportional to that. Okay, well, let's do an easy problem. At an amusement park, you and your friends sit in a large rotating disc. You sit at the edge and have a rotational speed of 4 RPM and a linear speed of 6 meters per second. Your friend sits halfway to the center. What is her rotational speed? What is her linear speed? So if you're on the same disc, then the disc is going one speed. It's going 4 rotations per minute. And all of that is the same anywhere on the disc. So the rotational speed is the angle that's changing in a certain amount of time. And no matter where you sit on that disc, your rotational speed is the same. Okay, so that's your RPM. Your linear speed is going to depend on where you're sitting. If your linear speed is 6 and your friend is halfway, then that means that it's half of the radius. Your radius is 6, and it's a halfway radius of 3, so her speed will be 3 meters per second. Yours is 6 meters per second, hers is 3. The last thing emphasized in this chapter is the idea of car wheels on a track. If you're going around a track, then your outer wheels have to be moving faster than your inner wheels. That's very cool. But what would happen is that you would, every time you went around a curve, if it were straight wheels, you would go off the track. So what's going to happen is if you want to go in a circle, you've got to make the wheels different sizes on the inside and the outside. So here's a paper cup, and if you spin a paper cup around the outside, because the inside has a narrow circle and the outside has a wider circle, then you are going to go in a circle. So the train car wheels are tapered, both of them are tapered, so that since they're tapered one on one side and one on the other, they they always center themselves. They can go on straight track just fine, and then as they go around the curve, they will ride up on the high part of the taper, and still then center themselves when they go back on. Somebody designed it really beautiful, but it basically works on rotational motion just like we've seen. So, final question. What is the relationship among tangential speed, rotational speed, and radial distance? We've already seen that if you have a circle, a disc, okay, your tangential speed is how fast you're going straight at any one instance. Your rotational speed is this idea of an angle being brought out at a certain amount of time. How much is that disc transplanting its angle in a certain amount of time? That's its rotational speed. Its radial distance is how far is it traveling. Okay, the reason why it has a higher tangential speed at the end is because its radial distance is farther, but you're covering it in the same amount of time. That means you're going faster. Okay, so its radial distance is around the radius of the circle, around the outside. How much distance is it covering? And it covers more as you go further, covers less as you go towards, and then since this is going faster in the same amount of time, it must be going faster as straight ahead.